Hello guys, in this tutorial we are going to model a vertical vessel with the help of PV-Elite software. First open the PV-Elite, click OK. Here's the vessel we are going to model. It's a vertical vessel with two semi-elliptical heads in the bottom and top of the vessel and a boot shell at the bottom of the bottom head, and you can see the configuration of the vessel, tangent line to tangent line, and the ID of the vessel is 1400. First we create an elliptical head, check the units, we name it as bottom head. Before we go through further modeling process, it is better to fill all the data in the data sheet of the vessel. For example, design pressure, which is 3.8, a full vacuum, and design temperature 110. We put these information in the design constraint. The design temperature is 110, and because the vessel is full vacuum, we'll leave this number without any modification. The vessel shall be analyzed with full vacuum condition, as the datasheet wants us to analyze this condition as well. The outside temperature or external temperature, we say it's 50 for this case. The next thing is to set the datum line. There are multiple options for datum line in PV-Elite, and the first option is bottom shell, seam weld, and the datum line is created from the distance we choose in the box from this weld line. But there are other options for setting this number as well, or setting datum line. Of course, there's a mistake for this vessel because the straight flanging is 35, but I mistakenly got it as 50. Another option is the datum taken from bottom left tangent or bottom of vessel, which has the same meaning as the lower option. I'll try to explain the difference between these two options in a separate video if I can. But now for this case, I choose the -50 for this vessel. Now I'm going to model the shell 1. This vessel has two shells. Shell 1, sorry. Now I'm putting all the information in the design constraint. For example, the hydrostatic test condition, which is anticipated in the datasheet for horizontal and vertical conditions, and the relating pressure is given in the datasheet. We fill 0.5 0.39 for the horizontal condition of the hydro test. We put the MDMT as 5 degrees in the datasheet. And there is an option for flange distance to top, which helps PVLE to calculate the height in hydrostatic pressure, and the service of the vessel is the vessel is manufactured with welding process, and the service type is non-toxic or any other category of this type. So we choose none because the service is hexagon and it's not considered as a lethal or any other options in this field. The degree of radiography has 4 categories, RT1 to RT4, and in this case, because we have a combination of hot spot and full radiography, it is better to choose RT2 for this vessel. And the explanation of each of the RT1 to 4 is in the PV-Elite manual. A spot for shells and full for heads. So it's better to click on RT2. Miscellaneous weight is the weight of the attachment we don't consider in explicit modeling in PV-Elite, and it has some options. You can choose the component for miscellaneous or give a general number for the miscellaneous. PV-Elite consider it as a dead weight when earthquake calculation is considered. The design code is division 1. And the number of MAWP is given in the datasheet, so we put it over here, 10.527. So we take the allowable 90% of yield for allowable in hydrostatic condition, as you can see in the PV-Elite manual. The allowable stress for hydrostatic condition is considered as 90% of the ambient yield stress. And some extra explanation for this situation is given in the PV-Elite manual. All done, we go to general input and try to set the dimensional properties of the bottom head. Now I should have give 35 for self-flanging, but mistakenly I didn't that. Sorry for that. But the thickness for the elliptical head is given as 12. We put it in the nominal thickness, and the after forming thickness is 8.5. and the nominal thickness is given because in this way PV Elite can calculate the real weight of the component. The corrosion allowance is given as 3 mm, and the material of the head is given in the datasheet as SA 560 carbon steel. The joint efficiency for head is given as full radiography, so it's taken as 1, as we will see in the PV Elite manual. Heads are full radiography. So as the explanation given in the manual of the PV Elite, we should take it as 1. Full radiography have joint efficiency of 1. Internal pressure is given as we put it in the design constraint. So it seems that all set for head, and we go through modeling the shells. We have 2 shells in this vertical vessel. Shell 1 with the length of 1500 millimeter and the thickness of 10 millimeter. Put a name for it, shell 1. The length of the shell is set as 1500, the thickness is 10, and we don't have any difference between after forming and before forming. And you can see the difference between thickness of the head and the cylindrical shell. And the joint efficiency shall be modified over here because the shells are not full radiographic and they are spot radiography, and ASME says that when we have a spot radiography for this type of weld joint, we have to set it as a 0.85. All the fields are set, and we go through the shell 2. Shell 2 has the length of 680. Create a shell, name it as shell 2. Set the length as 680. And the joint efficiency are 0.85. and the top head. Top head is an elliptical head, same as the bottom head, and PV Elite automatically set all the variables like bottom head.